All right, we'll try to finish this chapter up. I kind of rambled a little bit. All right, so again, eclipsing binaries are a wonderful tool that we use to calculate mass when there is such a eclipsing binary, which again is fairly rare, but it is a wonderful tool when it does happen. All right, so it's absolutely essential to determine what the mass is, because the mass really determines where a star will end up on the main sequence. We're getting a little ahead of ourselves, but right before a star goes on to the main sequence, it's before it actually becomes a star, it's called a protostar. And then, depending on how much mass it accumulates, will determine where it drops down onto this main sequence. So remember, this kind of curved line here is called the main sequence. There's of course the Sun, which if you go straight down, it's a G-type star. It has a luminosity of 1, and then of course if you go up here, here's a star. It's got a mass. If I had to guess, probably about 8 or 9 times the mass of the Sun, and then notice its luminosity is 100 times the luminosity of our star, the Sun. And then of course you have much smaller masses. In fact, this is the vast majority of stars, these M-class stars. But notice they're putting out less than 1/10, and in some cases like this, 1/100th, 1/100th the luminosity of our Sun. And in fact, what we're going to find out is these stars live much, much longer than these stars up here. So these stars have more mass, therefore they have more fuel, but they're burning their fuel at an incredible rate, right? That's kind of a way of looking at what luminosity is. Luminosity is the rate at which energy is pouring out of these stars. Right? And so, in these cases, these stars way up here are 100 times more luminous than the Sun, 10,000 times more luminous than the Sun, and so they're even though they have more mass, they use it up a lot more quickly. All right, so now getting back to these eclipsing binaries, what we do, and I kind of walked you through this with the in the last video about the shape of the intensity curve with time. And so basically that will give you orbital information so that you can use that in what's called the modified version of Kepler's third law. Kepler's third law was really about planets within our solar system, but it's been modified. Anytime one object is orbiting another, you can figure out the mass. Now, the thing is, when you have binaries, let me go back to this picture, even like this. Okay, so two stars orbiting each other. What Kepler's law does for you, so let's get back to this, is it'll give you like the total mass of the two stars, right? And then what you have to do is there turns out to be a linear relationship between the speed of the stars, which of course you get from the Doppler effect, and the mass. So you can get the sum of the two masses of the two stars that are orbiting each other, and then resolve what the mass of each individual star is by figuring out the speed, which again, of course, you do with the Doppler effect. All right, so as it says here, the speed is inverse. Oh, sorry, I think I said that wrong earlier. The speed is inversely proportional to the mass, right? So, for example, the faster it's going, the less massive it is. Right? So really tiny stars are moving a lot faster than really massive stars. All right, so that's how we break down the masses of the individual stars. So when we do a general survey and we're just looking at our galaxy, the Milky Way, here's what we see. So we have more than, close to, 41% of the stars are what are called red dwarfs. That is, they have less than 1/4 or 0.25 times the mass of the sun. Remember, we always do this. We always look at the stars and we compare it to our sun because that's the star that we know the best. And then there are what are called dwarf stars. That's about 28% of the stars that we looked at in our galaxy. Those are anywhere from 1/4 to a half the mass. And then there are these stars are actually considered dwarf stars as well. But anywhere from 0.5 or half the mass to 1 times the mass of the sun, you get about 19%. 8% you get 1 to 2 times the mass of the sun, and then you get anywhere you get about 3% of the stars that are anywhere from 2 to 4 times the mass of the sun, and then there's this little sliver here where you're going to have more than 4 to 8 times the mass of the sun. That's about 8% of the stars. Those are called giants. And then there are the blue giants that can anywhere from 8 to 20 times the mass of the sun. That's now you're getting down to 0.3%, and then more than 20 times the mass of the sun. You get to about 0.06. So that's extremely rare to find stars like that. But they're out there. I mean, there are stars that are 100 times the mass of the sun. All right. This is actually really very, very critical that we understand this. So there seems to be a relationship between this is all done in solar masses, like 1 times the mass of the sun would be right here, and then there's the sun, of course, and then 1 times the sun, so the radius of the sun would be right here. But notice there seems to be a linear relationship between the size of a star and its mass. So more massive stars, larger stars basically have more mass. I mean, there seems to be a 1-to-1 relationship between those two. And then it becomes even more interesting, and there's a stronger relationship between the luminosity in solar masses. Like, for example, the luminosity 1 would be our sun, and the mass in solar units again. So for example, if you have something that's 100 times more luminous than the sun, then if you draw a straight line down here, you find that these things are about 2 times the mass of the sun, or maybe a little bit more, 2.5, 3 times the mass of the sun. All right, so this relationship, and by the way, this is for main sequence stars. That's actually really important to understand that these relationships exist for main sequence stars. So it turns out that we can actually predict the lifetime of a star. So I was kind of hinting at that before when we were looking at the HR diagram. So the lifetime of a star is proportional to the mass, which is the fuel source, divided by the luminosity. In what the luminosity, of course, is the rate at which mass is being converted into energy, the rate at which the star is shining. And so these are always done in solar units, right? In other words, the mass, like if you put like 15 times the mass of the sun, and the luminosity is, let's say 20 times, or 40, 50 times the luminosity of the sun, you can figure out the age. Like, for example, and the way, I'll do some examples with this when I do the problems at the end of the chapter, as I always do. Anyhow, you take the mass in solar units divided by the luminosity in solar units. You usually measure those things, and then you multiply it by 10 to the 9th, right? And so, for example, for the sun, it's 1 divided by 1, and then times 10 to the 9th. In other words, our star is expected to have a stellar lifetime of 10 times 10 to the ninth, which of course is 10 billion years. Right? So, our star is 4.5 billion years old. It's got about another 5 billion, or a little bit more than 5 billion years to go. So more massive stars, they have much higher luminosities. You can have luminosities as much as 1,000 times the luminosity of the sun. And maybe 20 times the luminosity, the mass of the sun. Even though it has more fuel, it's using that fuel up a lot faster. And so you can have these really massive stars can last maybe 100 million years, a couple or 300 or 400 million years. But the really low mass stars, like M class stars, those stars have life expectancies that are actually even greater than the current age of the universe. The current age of the universe is about 13.8 billion years. 13.8 times 10 to the ninth years. And so when we do these calculations for M class stars, they'll be around for, in some cases, trillions of years. So that they're going to be around for a while. You can also use this relationship. It turns out that the luminosity is proportional to the fourth power of the mass, and so if you put the numerator in solar masses and the denominator, then the stellar mass divided by stellar mass to the fourth power, would be 1 over the stellar mass to the third power. Right. I prefer using this up here, the stellar mass divided by the stellar luminosity. This doesn't give you as good of a prediction. Let's see. So most stars, these massive stars, have very short lifetimes. So in the maybe tens of millions, in some cases hundreds of millions of years. A star like our sun, it's in the tens of billions of years, and there's some red dwarfs that have lifetimes in the trillions of years. Okay, and so you use this equation to make that prediction. All right, and so that ends our chapter. Let's just go over what we learned about. Just how much time I have? Yeah, I got a little bit of time here. We measure distances using parallax. That's the first way, and that's, by the way, that's been going on for about 200 years. Then we look at this apparent magnitude scale, and it's the apparent magnitude, of course, actually goes into the negative region now, because we have better instruments than Hipparchus had 2,000 years ago, and so we can relate the apparent magnitude to the absolute magnitude, and we can also determine distance that way. So absolute magnitude is what the magnitude of the star would be if it were 10 parsecs away, right? And so we do that mathematically. Obviously, there are some stars that happen to be 10 parsecs away, and so their apparent magnitude and their absolute magnitude are equal. If stars are a little closer, then their apparent magnitude is bigger. It was smaller, I should say. Right? Remember, apparent magnitude, the smaller numbers, like apparent magnitude of 2 compared to an apparent magnitude of 1. Apparent magnitude of 1 would be brighter. So you can compare apparent magnitude and absolute magnitude. Let's see. So the spectral classes are, that's that, OBA, FG, KM. We can calculate stellar radii if we know the distance and we know the luminosity. With main sequence stars, that's what we mean by normal stars. There are also, you also find red giants, supergiants, blue supergiants, as it says. There are also red dwarfs, and there's even white dwarfs, which I didn't really cover too much. These are actually stars that are dead. These are dead stars. They're just producing energy due to heat that's left over from their lifetimes. So the luminosity class